Yep. All right, rolling.
It is recorded.
Okay. Hey guys, hey everybody. Nice, nice to see y'all. Glad to be here. So today I'm going to talk about this thing called Aggregator Leaf Tailor and how we use it at theScore to bring data to our users with ultra low latency. I gave a version of this talk before at P99 Conf, and half of the story here is not Elixir. So I've tried to like strip out some of the other language, which we'll see is Java, and talk about the implications with Elixir. My company, theScore, is very heavy in Elixir. This one project is in Java, and we'll kind of talk about why it's that way as we go. Yeah, so like I said, name is Jeff Utter, staff software engineer at theScore. I'm a member of our platform team. So our, like most platform teams, our goal is to kind of build internal tools, services, things like that to help other teams do their jobs better, faster, more securely, et cetera, et cetera. I worked in Elixir for like 6 years, and I wrote my first line of Java in this job at the age of like 30 something. I tried really hard to avoid it, but it caught up with me, and I have since written some Java. And it's not as bad as I thought it would be. But I'm still an Elixir developer at heart. And I've spent about like 4 years working in sports media and betting, worked at Bleacher Report prior to theScore. And so we're going to talk about this thing called Aggregator Leaf Tailor. Here's kind of a table of contents of what we're going to hit today. What is it? Our goals that kind of led to this project I'll be talking about, and the project itself, which is called DataDex. For that, we have an overview, kind of cover the architecture of it, how we use that aggregator leaf tailor pattern in the project, then some performance tips we learned while building it. There's some Java stuff in there that's gone from this talk, but there's some interesting RocksDB tips. And then I'm going to talk about our watch feature, which is where the Elixir really comes into play. And then a wrap up. So aggregator leaf tailor. Also, hopefully it looks like the color, the purple on purple is working here. So I hope that works for everybody. It's our company branded slides. I think it looks okay. Yeah, there's a lot of purple throughout the talk. Okay, so the term aggregator leaf tailor, I hadn't heard this term in this configuration until I started this job working on this project. The term really seems to have been, I don't know if it's coined, but it was really pushed by the company Rockset in around 2019. Their product is built around this architecture, and they've done a lot of blog articles, talks, white papers that describe it. There's some prior art. These are all links to blog articles and papers and stuff, and there's references at the end of the talk. But there's some prior art, some talks or articles by Facebook called Science in the Social Graph. I think the first two are Facebook, and then a LinkedIn talk as well, where they use some similar concepts and a few of these terms, but the first time I could find it being referenced was by Rockset as aggregator leaf tailor. So what does that look like? The tailor component pulls data from various sources, and I realize we're talking about it in the other way. Data enters the system in reverse, I guess. The tailor pulls data from various sources, could be really anything where you have data being created. In our case, it's all fed by Kafka, but you could be pulling data from Kafka, I don't know, Google Cloud PubSub, S3 buckets, whatever you have. And then the tailors write that data into another component called a leaf, which stores and indexes the data. And then on the read side, we have aggregators that pull the data out of one or many leaves and then do any kind of aggregation, whether it just be like collecting the data, or it could potentially be doing some mathematical aggregations or something like that over the data. So what were our goals, and why did we kind of lean into this pattern? So we want to build a low latency distributed data store that developers actually want to use to access materialized streaming data. So more specifically, our goals were low latency, consistent latency, low operational complexity, has to be easy to maintain, easy to deploy. We want it to be scalable, both horizontally and vertically. We want organizational scalability. This is really important, that we want many like teams to be able to adopt it with very little friction. And we also care about developer ergonomics. And all of this is kind of fed by the fact that if you're building internal services like this, like they have to be better, not just in performance or some kind of technical metric. They have to be better than the alternatives in ergonomics too, right? No one's going to pick up your like bespoke internal in-house service that who knows how reliable it is when they could just go grab Postgres or something, unless you have a really good value prop, and that includes making it easy to adopt. So that's a huge important point for us in developing this. And then jumping back a little bit, I mentioned consistent latency. This comes into play because we use GraphQL a lot. I think almost all of our mobile front ends use GraphQL. And if you've ever used GraphQL before, they have this like data loader pattern thing where rather than like with Postgres, you might go to your database and have this real specific query where you join everything you need and you get it all back in like one very nicely formed lump. With the data loader pattern, you may end up doing like a bunch of small queries. You might, in my head, it often comes out kind of like tiered in like a triangle, right? You like grab your user and then your user has many businesses, right? And then you grab like, you do another query for all the businesses where the ID is in the IDs you grab from the user, and you kind of tier this out. So when you're doing multiple queries sequentially like that, you hit those P99, they're no longer 99th percentile, right? Like you end up hitting those bad latencies often. So it's very important for us that the latency is not only fast most of the time, but like all of the time, because users are going to feel that if it's occasionally poor. So besides our goals, we have some constraints that are pretty interesting. We operate, so I didn't cover this before, but we're a sports news media betting company. And the betting part of the company has some really interesting constraints wherein I think it was in, I'm not gonna go with the year, I'm gonna botch it. Maybe 2018, the federal government in the United States removed some legislation that prohibited sports betting online, and each state could kind of make their own regulations, and a few states have, but each state has their own governing body for the betting regulations. And some of them include things like geolocation about your users' data and their transactions. So like, I don't know the specifics, but a hypothetical example is that like, if a user's in Indiana, their data or their transaction data can't cross into Canada or something, or even outside of Indiana. I'm not sure which states have those kind of requirements, but they exist. So we have to operate in every state and province where we do business. Some of them are lucky enough to have a official like AWS or Google Cloud data center, but a lot of them don't. So we have to be able to operate our service on not self-hosted infrastructure, but other infrastructure other than the main clouds. And with that, you start losing out on a lot of the really good managed hosted kind of services. Like, you know, you can run your own Postgres. RDS is like a step up, but Aurora is like way more scalable automatically and things like that. You know, MongoDB Atlas, they all take this like really user easy approach. You pay for it, right? But we can't use those because they don't necessarily operate everywhere that we need to operate. So that cuts out like a whole class of like, well, couldn't you just do this with, you know, put it in, or like CockroachDB or something? Well, you can run that yourself, but do you want to run that yourself? And their managed solutions probably don't operate everywhere we need them to. So, and then also back to constraints, developer ergonomics is right. If it's not easy to use, nobody's gonna adopt it. So,
Sounds impossible, Jeff.
yeah, it is. We will solve this. So there's a hypothetical ideal in kind of streaming applications. This is what like, I feel like when I was a younger developer, I heard talks about this and it seemed like super nice. And then there's a bunch of things that they don't tell you with these kind of solutions. So the kind of ideal world is like teams operate independently. They publish data onto some kind of global bus or event log or something, right? It could be RabbitMQ or Kafka or whatever. Other teams who know nothing about what the first team's doing just read that data off and they do whatever they need with it, right? They maybe suck it into their own database and write it to their own database. And it's streaming, so it's low latency, and the data is now stored in everybody's application, so it's fast and nearby and low latency. But there's a lot of drawbacks that they don't tell you when you start thinking about these kind of systems. And there's like number one, there's a ton of hidden coupling, right? If team A that's publishing that data all of a sudden changes their schema and somebody was depending on that downstream, well, now you have a problem. And if you use something like internally, we use a lot of protobuf with Kafka schema registry that can put some guardrails on it, but then, okay, maybe you didn't break another team's thing. Now you have a bunch of communication you have to do. And we don't completely alleviate that problem. That one's still going to exist. But these type of systems inherently have a lot of coupling between teams. And then also each team has to come up with a bespoke ingestion process, right? Each team has to decide, well, what library are we going to use to connect to the Kafka, and how are we going to ingest that data, and how do we write it to our database? And I don't know, like how do we optimize our database and make sure it's right sized and all those good things. And then they also have to figure out how to index it, right? What indexes do we need on this table to get the fields we need or whatever? How do we join it with our existing data sets? And the implementation of each team also, like the latency there for them to get that data depends on each team. They might, one team might have a ton of time to optimize those queries and make sure it's super fast and performant, but another team with less resources is going to pay a penalty because they can't, they can't optimize that. And maybe it's okay, but maybe not, right? It'd be great if we could solve that problem for everybody. And then there's also hidden coupling that I didn't mention. Besides just the data structures, right? If team A all of a sudden pumps out like 10 times the amount of data because they hooked up a new data source or something, then every downstream from that now has to absorb that load, and maybe they weren't prepared to handle all that data. They don't have their database scaled up enough. They don't have enough resources behind it. So here's our problem. We want to solve this. We want a system where we can help developers kind of fall into the pit of success, right? Teams still publish their own data. We know there's coupling. We kind of acknowledge it up front using Kafka schema registry. There's a protobuf, and there's a library called buff, which is like a linter, and it can make sure that when I'm changing my protobuf that like it's not going to break. It's not going to be a backwards incompatible change. It doesn't know what the other teams are doing with your data, but you can enforce some rules, like you can't change field names or change the type, things like that. So you have to, when those problems arise, you have to address them up front and do that coordination step up front before you mess something up for someone else. We want the way that people ingest the data to be uniform across all the teams. We want to kind of abstract that away from each team so they don't have to think how they connect to the Kafka and how do they do that reliably. We want the indexing process to be kind of abstracted away and declarative, so people don't have to figure out, do I need a GN index or a B-tree index, right? We don't want people to have to think about that. And then ultimately, the data can't live in their application directly in this type of system where we're solving it for everybody, but we want to expose it through a simple gRPC API that makes sense. And the key to making it fast is we want this data to live. It's not going to live in their application, but it's going to live right next to it. So each team that has an application that needs access to this data runs, you can kind of think of it like a sidecar in like the Kubernetes kind of world. They run a copy of DataDex next to their application. So you get really low latency. It's running in the same data center on the same maybe on the same hardware, maybe not. You could, if you wanted to, you could run on the same hardware. So you get really low latency, it's using gRPC, that's all great. So I already said the name of the project. It's called DataDex, and I'm going to kind of hit on the architecture of it. We kind of have a hub and spoke architecture because I was talking about those like geographic restrictions. Some data can be global. For example, I don't even know if this is, fortunately, I'm kind of removed from the data that people put into our system. I'm just building the system. So any of my examples are totally contrived. But you can see on the right side here, we have a hub, and that might have services that have data that is globally okay. Like could be sports scores or something like that, right? And then on the left side, we have the spoke, and this is what's running in each geographic region. There's a lot going on here, and we'll break it down with some nice arrows and things like that. So the data flow looks kind of like this. Client writes some data into a backend service, and then that backend service does whatever it needs with the data, publishes either an event or some change data capture kind of stuff to a Kafka topic. The tailors in DataDex read that data off the Kafka topic, store it in the leaves. And we're done as far as the right side of things. The read data flow, we get to ignore that whole, like half of that chart. Now we're only concerned with this little bit here. We have, so when a client makes a request, it goes to a backend service and says, hey, I need some data. That backend service then goes to the aggregators and says, hey, I need that data. The aggregator figures out where it needs to go, what leaves it needs to grab that data, pull it back into the aggregator, does whatever it needs there, and back out to the backend server and ultimately the client. Technology stack. So this is, I said, this is our Java project, right? We chose Java for a few specific reasons. One, it has great library support for everything, like first-class library support for all the stuff we need. Has great Kafka, like all the good Kafka libraries are in Java, right? Has good gRPC support, and has like RocksDB second to the C++ implementations, like Java's #2 support there. Elixir supports all these things, but like the quality is varying, and we didn't want to have to like go rewrite a core library like this or something. Yeah, we also chose what was I gonna say? We also chose Java over like Kotlin or Scala or another JVM language because it's like super easily cut and pastable off Stack Overflow. Right? There's a lot of resources out there for Java and for these libraries in Java, rather than like if we're trying to figure out some RocksDB internal, having to figure out the Java API and then like convert it to Kotlin. Since we built like V1 of this, we are looking into Kotlin a little bit. It's in my opinion, a nicer language, has some nice abstractions over concurrency stuff that are a little bit easier to deal with than Java. But yeah, anyway, so we're using Kafka for the Taylor thing. All our data pretty much end to end is stored in protobufs. Like the clients use GraphQL, but after that, everything internal is in protobufs. We use RocksDB to store the data in the leaf. And then I mentioned Kubernetes. That's really important for the developer ergonomic side of things, which we'll get to in a moment as well.
So Kafka is reading Kafka?
Oh, the Taylor is a Java thing that's reading from Kafka. So then how do we use that pattern to meet our goals? On the low latency front, we're using Java, but we're using the ZGC, which is a newer garbage collector that promises like sub-millisecond pauses. Because we all know like that's a big thing with Java is those garbage collection pauses that can destroy your tail latencies. ZGC seems to solve that. We're also super careful with memory allocations. In a lot of cases, we like allocate buffers to store the data that's coming out of RocksDB once per thread. We read into that and like reuse the buffers a lot. It involves like a lot more, I don't know, like fiddly buffer manipulation that I care about. Like you write the buffer and then you get some new data in, you have to like rewind the buffer and rewrite it. And it's kind of a pain, but it lends itself to, you know, really low latency because you're not having to allocate memory on every request. And then we're also using gRPC streaming, which is, I don't know if y'all are familiar, so I'll explain a little bit. gRPC uses HTTP2, which is a streaming protocol. So you open like one or multiple connections or pool of connections, and you can reuse those connections, but each request has like headers and a bunch of stuff that goes with it. With gRPC streaming, you make one HTTP connection and then one gRPC streaming connection, and there's like no headers and like no overhead essentially, other than like the network latency from point A to point B. It's great. I mentioned it's a double-edged sword because it bypasses like all the normal HTTP things that we know. So like if you're using a load balancer in between, you end up with one connection from service A to service B, and that's it. You won't go service A to a load balancer. You can go through the load balancer, but it's still a single connection. It can't like fan out because it has no idea what's happening in that connection. So then that puts a little bit more work on the client side where you have to like build pools, figure out when you need to find new nodes and readjust your pool, things like that. But the end result has been pretty good for us. For low operational complexity, and this is where we cheat a little bit. So it's a single code base with kind of two deployable units. So Aggregator Leaf Taylor talks about 3 components. Right now for us, it's 3 components, but they're in one one executable. It's kept it really simple. Don't have to deal with a bunch of like sharding problems and consistency problems if you're Especially because we're feeding off Kafka. Like if you make a write and let's say you have to write out to 3 replicas, like how do you know that all the replicas work successfully? And if you have data that could be parallelized, you have to, you have ordering issues and stuff like that. If we were dealing with some sort of distributed system, so we're cheating, each node is a full replica. It does all 3 things, has all the data, and it's worked really well. We've written it in such a way that those components could be split apart down the road if we need to. But right now we don't need to, and it's it's made it a lot easier. There's two deployable units. We have the DataDex application itself, and then a Kubernetes operator, which I think I have a slide about later because that's a big part of it. But yeah, so we run more or less 2 processes, but only one is doing the actual work here. On the scalability side, we have this like fast snapshot backup restore mechanism where periodically one of the nodes will take a backup, upload it to some kind of blob storage. And then if we need to scale up for more read capacity, we just add a node rather than having to like replay all the history of Kafka since the beginning of everything to get to the current state. We can just download a snapshot, replay the last few minutes, and we're caught up pretty quickly. And then we can just add nodes and scale out that way at the cost of compute and disk. Future improvements here are eventually we're going to have to split these out into separate components because we probably won't be able to hold all the data sets in each node. I should mention, this is probably a good place to mention it. A lot of places that use this type of pattern like Rockset are kind of built for analytic workloads. This isn't analytic workloads for us. This is like your normal kind of web app user data. We have a lot of data, not like every time someone clicked on the screen level data, right? So eventually we're going to have to split it up though and deal with those fun concurrency, consistency type issues. Okay, and then developer ergonomics. This is where I mentioned we have the Kubernetes operator. So we have a CRD and the teams that need to deploy a DataDex, just deploy a single YAML file describing their instance. We'll look at one of those in a second. We also provide an Elixir client library. Like I said, most of the developers at theScore write Elixir. So we've kind of wrapped, I mean, it's gRPC, so that handles a lot of it. The gRPC libraries generate a lot of that for you, but we've wrapped some of it into a nice library. We have a pretty simple query language. CRD example. So this is, I stripped out some stuff that's not useful, but essentially it looks like this. Maybe I'm missing an earlier slide, but it's basically like your average Kubernetes thing that has like the API version and stuff. And there's also a section for resources, which looks a lot like the type of resources you would apply to a pod or a deployment. But nested in there, there's this part called the collection. And this is how users define the data they want in their database. So they give it a name. This is game scores. You tell it what Kafka topic you want to look at, and then what indexes you want. So teams need to know how their data, they need to know the queries they're going to make up front. We make it pretty easy for them to add indexes and remove them and change their queries as they develop. But it's not like Postgres where you like have all your data, and then you can just make whatever query you want, and maybe it's indexed or maybe it's not, and you don't really know until the performance is garbage. Like you have to know up front the queries you want to make. So the indexes have names. So in this first example here, you have like, we're getting game scores by team date or by team and date descending. You'll see the expression that's like the actual index. So we're just saying we want the team field off of the game score protobuf, and we want the date field, and we want it sorted descending.
You add another index later, does it retroactively?
Yep. Yeah, we've worked on this whole migration system that'll essentially just like re-ingest the data. It just kind of sucks it back in with the new definition, and therefore it will create the new indexes because they're defined now. There's a lot of tricky concurrency stuff there because you have to deal with like let's say you had, because it's Kafka, right? And you end up processing like the whole history of things, sort of. So if you have a record that says like, I don't know, my username is Jeff, right? Or something like that. And then, yeah. So my username is Jeff. And then I go to reindex and it's like reprocessing the data it has stored, which says my username is Jeff. But then a new message comes in and says my username is actually Joff with a G, right? You could potentially have issues there where like you loaded the name Jeff and then the Joff came in and then you wrote the Jeff over it or something like that. So there's a lot of fun concurrency problems in there. We have to use a lot of mutexes and stuff, and I think it's in a good state now, but it took a while to get there and to sort those kind of problems out. Any more questions there before I go on?
Well, I guess the reverse question too, but it sounds like they drop an index.
Yeah, it just,
I guess probably people aren't taking care of their stuff well enough.
yeah. And right now, I honestly don't think we even permanently, if you delete, like if you say, I don't care about this game score topic anymore, I don't even think we clean it. We have a thing that like marks it deleted, but it's still actually there. But this has only been in production for maybe 3 or 4 months now. And I don't think teams, maybe in development environments, people are like adding a thing and like testing out indexes and stuff. But once stuff gets to production, like it's pretty stable and they're not making a ton of changes other than maybe adding new indexes as they need new data. But it's not, at least at this point, not frequent that people are like, you know, that data I thought I needed last month, I don't need it anymore. Right. I'm sure that'll happen someday, but it's not a big issue yet.
Can I ask a database nerd question?
Yep.
So you're basically creating additional value stores for each index.
Yep.
Are you storing the whole payload inside the index,
Just,
or
yeah,
you
just the primary key.
Okay.
So if you're looking up something from a secondary index, it's 2 hops, but it's fast.
Yeah.
And I'm trying to think. So they're not actually separate. In RocksDB, your like database is called the column family.
Yeah.
It's still in the same column family, but it's just like a different prefix on the keys or something. Right. You know, before working with RocksDB and stuff, I looked at and was really interested in things like Cassandra and what's the AWS Dynamo, things like that. And I think you have to model things a lot in the same way with RocksDB because all it gives you is like keys and values and range scans. I never like got to use Cassandra or Dynamo in Anger, but now I'm getting the taste for some of that. Okay, cool. So once we have these indexes made, this is what the client library looks like. We have this thing, we have like a store thing that's kind of global, and we say, we want to list stuff from the game score collection, then the index we want to use, which was by team, date, descending. And then we kind of fill in the blanks of that index, right? The index had required team and date. So we say we want teams where the name's the Royals, and we want dates that are greater than equal to, this is a variable, 7 days ago. Somewhere I calculated what 7 days ago was, right? And I pass that in. And then we have some options. You could say like limit 5 or things like that. And that's all the clients need to know. And they get back payload of the data that they requested. And yeah, have slides walking through that. We don't need
The
those.
second argument is mandatory.
Yep, that's the index. Well, sorry, nope, I lied a little bit. You can just grab things by primary key if you know, like if it's the user's collection and users have an ID and that's the primary key. And I think the primary key is always the ID. I don't actually have the syntax offhand, but then you would just say, I want game score or like users with the ID, and it'll grab it from the primary key. And then I feel like we saw this slide already, didn't we? Oh, this is just going back and showing that like these, the expression kind of has like the variables in the index that you need to then fill in here. So we have to give it the team, Royals, and the date. And there's a bunch of operators you can use for like greater than, less than, in, not in, those kind of things. Some of them we're able to optimize in RocksDB and like create smart range scans for. Other ones we have to like pull out a bunch of data and do it in Java. And I'm sure there's optimizations we could do there too.
Does that tell you your latency?
Nah, well, I'm sure for some places. It's nowhere that any team actually cares. Like maybe for some admin stuff, I think there's some admin panels that like load a bunch of data and are like sort of infinitely sortable. They're like, oh, we want to sort by every field and every combination of fields, which becomes problematic in things like RocksDB, because the way you create the indexes, you would need an index for every possible combination of fields. So I think there may be some places like that where it's maybe a little slow for back office kind of stuff, but for all the user facing stuff, we haven't really run into many problems. The one thing we might be able to do is people have asked us for, I can't remember the exact query scenario that led to this, but partial indexing. We don't really have partial indexing right now. It might be like, I want all games that are in the open status in Kansas or something like that, where like that, where there's that status in the middle. So I never care about games that are in any other status, but I need that like open status in the middle of the query. I'm getting a little bit too deep into the way that we organize our indexes, so it's maybe not so relevant, but partial indexing is an optimization that we can definitely make some use of. Cool. Talking about internals of RocksDB, one of the optimizations we did to hit a bottleneck like this is to ruthlessly narrow your search range. And I'll try to explain what I mean here. But the way the data is stored in RocksDB is it stores all the recent data in memory. So it's like really fast to look up, but after a certain, I think it can either be time or a certain like amount of memory usage. It'll write that data in what's called SS tables on disk. And there's also layers of SS tables depending on like the age of the data. So when you do a lookup, it's like, hey, is this in memory? Oh, no, it's not in memory. Let me go to the first layer. Oh, it's not there. Let me go to the next layer. And they have internally, you can use like a Bloom filter kind of thing. So it'll like, it can tell you really quick if it even needs to bother checking that layer. But besides that, when you do a range scan, it has to like load all those intermediate, all the layers. Range scan being like when I say I want everyone whose name starts with Jeff, right? You would scan from the beginning to the end of everyone whose name was Jeff. But it needs to check memory, it needs to check the first layer, and it has to check all those layers because it can't just like jump to the right place. So where this becomes problematic are inquiries. So for an example, this query. So I want all of the players, the index is players by team and their position name. So I want all of the players on the Chiefs who are either defensive back and quarterback. The way this would be stored in RocksDB looks like this. Essentially, the pipes in the key aren't necessarily there, but you end up with the first part of the key being the Chiefs. So if you want all the Chiefs, you can jump right to the first place there's a Chief. It does like a binary search and finds the beginning of that. And then you can just scan until there's no more Chiefs, until you get back something different. But when you have that inquiry and the field you need to do your in on is in the middle here, you would, like in one query, you'd still have to scan all the Chiefs and only pluck out the players that match that criteria. And it's extra bad in Java because each of those values has to cross the JNI bridge and have a memory allocated. So you're like, give me the first key, okay, and then it's like, oh wait, this one doesn't match. So now give me the next one, or it does match. So give me the next one and keep giving me keys, and then it'll filter out the ones that don't match defensive back or quarterback. But there's a big penalty for moving data out of C++, RocksDB, and into Java if you don't need to. The benefit here, what we kind of did is you can break those queries down into multiple queries that can jump right to the correct, it can do a binary search and find the part that you need for the inquiry. So you can jump right to the beginning of the Chiefs defensive backs, read them all out. You still have to cross the JNI bridge, but it's for data that you actually wanted, not data that you didn't want. And then once you reach the last defensive back, you can jump right to the next part of the in. And I think I had a little, before this type of query in some probably totally fake benchmark was like almost 2 seconds to run these queries. And after this simple optimization, it was like under, like the P95 is like 0.6 milliseconds, which is like, it's like drastic. And I think this was like in a staging environment, so it's not exactly apples to apples, but I mean, come on, that's a big.
Okay, so go back one or two. Sorry if I'm interrupting.
No, go for it.
So let's say you do an inquiry for C, D, and L. So we've taken out 3/4 of this approximate screen, like where the binary search is. I think it's probably less than.
Yep. Not that smart yet.
Yeah, like and that's yeah, but that might be something to think about.
Yeah, definitely. We don't have any like statistics or anything like that on the different columns in the index or anything like that. But that's a good point, that there are probably situations where you would get into those situations. I think like Postgres kind of optimizes that away from you, right? Like when you do the explain and it's like, oh, I thought I have an index for this thing, but it still did a whole table scan. Why? Well, it probably knows better.
If you're lucky,
Yeah,
if you did do something stupid.
right,
Yeah, it's just for us today.
right.
Yeah.
And then, yeah, I feel like I had this slide in here twice, so you're gonna get it twice. Yeah, so the aggregator leaf tailor pattern, it can help you normalize stream materialization across your organization, right? That's what we did. Like each team doesn't now have to figure out how they're getting that data off that stream and into their application. They still need to know how to make the queries, but they don't have to worry about storing it, indexing it, scaling their storage or anything like that. And it's infinitely scalable in that as long as you have dollars to pay for the CPU and disk space, you can scale out. And then, yeah, and we can run these leafs in every state. There's probably some scaling considerations where like, as far as the load you put on Kafka, we haven't really had to deal with those yet. And we might need to like do like replicas of replicas or something like that. Problem we haven't had to address yet. It's just working just fine, shilling over dollars to one of the major Kafka providers. And it's helped us achieve really low P99s. And then could have sworn this next slide was before, but the feature where this really comes in cool with Elixir is we have a watch feature, which I think I briefly mentioned before, but didn't talk about. So as data is being written to these collections and these indexes, we can set up a watcher on that. And it's over a gRPC stream where you can say, I want all updates for patron whose ID is this UUID, or I want updates for this game or something like that. And you set up in Elixir in our client, you set up something like this. I think you have to use Broadway, but you set up a Broadway watcher and you give it a module to do things with. And then in your handle message, you can, you'll get messages back from the watcher in your Broadway producer. Anyway, you can use it like this. So you have your patron ID, you can tell it to start watching that patron ID and your process will get all those messages from Datadex as the updates stream in. So now we're streaming from some backend application, wrote some data to Kafka, that streams into another state and writes data into a Datadex instance that your application has a watcher set up to. So now it streams down to your application. And to take that even further, we can hook it up to GraphQL subscriptions. And personally, I don't do much GraphQL, so I'm gonna like gloss over some of this code. But you can use GraphQL subscriptions and set up a field that has a subscription, has this like config subscription function, which when you're setting up the subscription, you start that watcher process, you give it the patron ID, and then it'll stream back those messages and send them out to the GraphQL subscribers. And we do some smarts under the hood in the client library where we like, if you're looking for, like if there's like 1,000 users that one machine's watching, like I want all the updates for these 1,000 connected users, it'll like batch them and like pool them into, so there's less watchers on the back end. Because the back end has to get all the updates and like filter them out and say like, is anyone watching this? Is anyone watching this? Is anyone watching this? So we do some smarts there to make it more scalable. But it gives us basically round trip user all the way through our servers, through different states, back out to the user in a different service, even watching their data streaming from end to end. So that's the end of the talk, basically. I mentioned there were resources. I'll put these slides up somewhere. I'll share them out. But these are the talks and stuff that mentioned aggregator leaf tailor that I found useful in learning about the architecture. And this is the actual last slide. So I'd be happy to answer any questions or talk about unrelated things.
Can you do approximately a full slide? Like massive architecture diagram.
Oh yeah. I think it's a little bit more than fourth, but
Okay.
this no.
Yeah,
wait.
That's the one I want.
Oh, okay. No, I'll go to the big one. Okay. Wait, it's not. Sorry, it's not synced. Okay, there we go.
Okay,
Got it.
so Specifically on the state hosting problem, that you scale the needs, because the data needs to, live in, customer data needs to live entirely within the state.
Yep.
If that's your specific concern. Why wouldn't you also need to worry about the tablers? Why?
So, yeah, okay, you do. In our case, they're all one process. So when you scale any part of it up, they all scale up because we haven't split them up yet. But yeah, that's definitely a situation you could get into. And honestly, right now, it's literally so it's Java and we have like separate processes within our application, within Datadex. There's one Taylor process that watching all those Kafka topics, an easy optimization. If we need that extra write throughput, we could start one process, one Kafka one Kafka consumer per topic or per partition or whatever. So far, the end to like round trip latency, at least as long as you're in, if you subtract like crossing the continent, is pretty quick still. So we haven't had to dig into that Taylor latency yet.
I think it's a really interesting pattern. Of course, like I will that's about Rock TV, this is totally, yeah.
Okay.
Which Rock TV was the successor to totally, but you know, like how if you had to do this differently, something like what I started bespoke OLAP database, but
well, I don't know what I would do. I can tell you that Rockset has this concept they call converged indexing.
okay.
And they explain how it works. Basically, they index everything. I don't know if it's reasonable for, like they come up with every possible index and write those. I think the indexes end up looking pretty similar to ours, except for they've created all of the possible ones.
Right.
I think I have never used Rockset, but my understanding is that they're used for like large scale analytical things. So you can like really quick, because of the cloud, load, terabytes or petabytes of data across machines, and you can load it up really quickly and execute some queries, and they'll execute really fast because it can parallelize it, and then you can shut the whole thing down or scale it way back. I think the storage requirements there would probably outweigh at least for us, because we're really concerned about the user, latency. And we know the development cycle, right? These queries are kind of defined ahead of time. And if someone does need to do like different queries, more like exploratory or analytical query across our data set, it's probably the wrong tool. Like we'll load it all into Redshift or something, and people like, that's a common thing. I think analytics teams tend to like Debezium all your data out of your database into a Redshift, and that's how they do those kind of queries. Yeah, so I don't really think we'll ever have much need for that kind of ad hoc querying.
Second question, have you looked at Materialize?
No, what is it?
It's the timely data flow software.
It's just called Materialize, like spelled normal.
Yeah,
Okay.
you might really.
I'll have to look it up.
It's more of a common question, but.
Cool. Yeah. And so that does what? It does similar.
So you define your indexes as they look like SQL queries.
Okay.
But what they produce but it's all from streaming data. So
Okay.
you think of like a streaming data, which is almost what you kind of figure too.
Yeah. And is it actually material? Like I'm assuming because of the name, it's actually materialized all that data ahead of time, and it's not like.
It also does differential dates, so you don't have to readjust.
Okay. Okay. Interesting.
That's probably not.
Yeah. Now that you mentioned that part, that sounds familiar. So I wonder if I have heard of them before, but definitely not since I started this project.
This is totally cool.
Yeah. It's been fun to build, even if I have to write some Java.
How many people are working with this?
It started with, before me, it was just 1 or 2, and the team's like 5 now. We've got a bunch of, our platform team handles a bunch of stuff. This being one thing. Another thing we do is like way less glamorous than this, but I mentioned the regulatory requirements. So we have a piece of software that sits in our Kubernetes cluster, scans it every day to send reports to the auditors, and also kind of gatekeeps deployments. We have a release management team, and if they haven't, like in production, if they haven't blessed like a specific SHA for the Docker container, it won't deploy, because that's what we've sent to the auditors and things like that. So we do things like that. We have, I didn't mention it, but it's totally related, is we have a Kafka library, like most companies end up wrapping Broad or something, or Broad. We have one of those. It handles a lot of stuff. It handles dead letter queues. We have an outbox producer in it, things like that. So we maintain that. And a handful of other like internal libraries and stuff. So I wouldn't even, maybe like 3 or 4 people have been dedicated. Like if you averaged people's time out, you could say maybe 3 or 4 people have worked on it.
And do you plan on open source?
Yeah, we haven't talked too much about that. I don't think anyone would have any personal reasons not to. I would love to. I don't know if there's any red tape reasons because of the regulatory requirements. I don't know if there'd be any problems with that. Also, I mean, so we just had like our 1.0 production release, like, I don't know, 3 or 4 months ago that it went like live in production. So we probably want to give a few more cycles on it and like get it, like we're happy with how it's working, but it's kind of funny open sourcing a big project that has a lot of time behind it versus like, well, here's my hobby project that I started open sourcing, right? So you really want to have a good showing if you were to open source it, but there's nothing or very little in here that's not generic enough that like people could use it in other situations. I guess the specific stuff is it's tied to Kafka and protobuf. So if you're not using protobuf, like we'd have to write a new adapter for stuff.
Are the Elixir apps using gRPC box, or are they using the
Elixir gRPC, and a few times we've talked about changing or writing our own, because Elixir gRPC kind of stalled development for a long time. Just recently, it's kind of gotten reinvigorated. So I think it's doing okay for us now that it's kind of gotten more active maintainership.
You can always switch to Go. They have a great gRPC library.
They do.
And then Go.
I mean, if I had my way for something like this, I'm hesitating because I don't know about library support, but language-wise, I think Rust would be a good fit for something like this.
materialize it written across that?
Oh man, I'm gonna have to go look them up.
You know much about that part of it. Yeah, someone can't see.
I don't know how it gets routed. I guess probably just probably DNS, I would guess. I don't think it's like if you go to theScore.com and you're in Kansas. We do use, so on the client side we use, I don't know if I can say any names out loud. We use some third party that does like location verification. So if I'm registered in Kansas and I go over to Tulsa and I try to place a bet, it won't let you. And I think it's smarter. I think they have other ways, like additional ways rather than just your IP to track you down. And honestly, it might make you grant location access on your phone. Like if you don't grant the application access, it might not let you. I'm not sure about that, but I feel like it does that kind of stuff. Honestly, for me, it's a little hard because most of the stuff we're running right now is in Canada, and it's hard for me to access our stuff because of the geolocation stuff. So as far as like actually using the app and placing bets, I don't, not that I actually legally can't make money off our own app, but as far as even testing the app itself is kind of a pain because it's like I have to get my IPs whitelisted in a bunch of different places and stuff like that. But yeah.
So do you actually have data center like a low for
Trying to think. This
or that was really recent. That was like a month ago.
yeah, I don't, maybe, no, I don't think we do yet. But interestingly enough, some, I've heard this, I don't know how true this is, but some states like actually make you have, like it has to be on your property. So like if we, I don't know if we're, I don't know if this is true, but I've heard this bit of information that like in some, like it would have to be in your casino in like the back room, something like that. And I do think I've heard that New Jersey has this like pull the plug part of like their requirements where they have to be able to go into your data center, and they actually do this. They pull the plug and make sure that they can't use the app anymore. I've heard that. I've never experienced it firsthand, but
That's a whole different level of chaos.
yeah, right. And the whole regulatory thing is fascinating. I had to get a gaming license in the state of Indiana. They have one of the more strict regulations. Even though I'm never going to set foot in Indiana or any casino in Indiana, and I won't be working in one, but because my company has, I think they have brick and mortar casinos there. In order to work on certain things that require certain levels of clearance, I need to get a gaming license there, which is extremely difficult too, because there's a bunch of places like the TSA pre-check places that'll like do digital fingerprint cards. They won't accept digital. You have to get an ink. It can't even be a scan printed in ink. You need like ink on or finger on ink pad. Old school fingerprinting cards, which you can't get anywhere apparently anymore. I had to drive to Manhattan to their like the K-State Police Department does it. That's the only place I could find. Yeah, yeah. I think in Topeka, the sheriff's department will do it, but only for a concealed carry permit. So if I was like, hey, I got this gun, I want a concealed carry permit. Will you also, can you do another one for my gaming license? Like, maybe I could have gotten it there, but otherwise, yeah, even the police department doesn't do it. None of the commercial places will do ink. So that was a little hassle.
So does somebody who wants to troubleshoot an issue with this system on customer data in Indiana have to physically be inside of Indiana?
No, but you'd probably need clearance. Like you probably need that gaming license to get the clearance. Yeah. Yep. Fortunately, I don't have to think about those things very much. Someone else thinks about them and just tells me what I need to do. And day to day, it's not really a pain. Like prod access is maybe a little locked down more than like previous jobs have been. But you know, we can get everything we need to do our jobs.
So I feel like we brushed over the aggregator today. Can you do showing across in the aggregator?
You could. Ours doesn't. Doesn't yet. I think the aggregator will become more critical once we need to scale our data out. Like if we need to shard or do some kind of persistent hashing or something like that, or sorry, consistent hashing. That's one place where the aggregator needs to know like, oh, okay, well, you connected to this node, that data you need's over in that node and that node and that node. Let me go aggregate those and bring them all back. I think if you're doing analytics, the aggregator would also play a bigger role where like I need to, I don't know, sum up your gambling totals or something like that, right? So it would like grab all your bets and then sum them up. We have had some requests from teams for like simple aggregations like counts and stuff like that, which not sure yet if we're gonna if those requests are gonna be important enough, but then B, if we want to like do that in the aggregator component, or if we just want to kind of pre-compute the stuff that we know we'll need, some like basic metrics like counts and things like that.
You might also be interested in the scuba.
Scuba spelled like snorkeling, like the underwater.
Yeah,
Okay.
from Facebook.
Okay, I'll check these. I need to.
They have a super dumb free aggregation strategy, which is send the query to every node and wait and see what comes back. So you don't actually have to know this.
Oh, okay, that makes sense.
But you have big fan outcomes. Their solution was, well, we don't let it take this, it's all memory.
Well, and honestly, that's an interesting thing that I found with RocksDB is like between the stuff that's stored in that top layer and page caches and stuff, if you give it like we have some graphs of disk IO, and most of the time we're operating and there's like no read IO. And I was just like, wait, what's like something's wrong. We're getting like I don't know how many requests a second. We're getting like a lot of requests, and what's happening? Like, oh, well, it's already loaded it all in memory between, RocksDB caches, the mem tables and page caches and stuff. There's nothing to read off the disk.
Yeah, just be careful when you actually get sets bigger. Things will later.
Right.
Yeah.
Well, and I think we're probably, we don't need to, at some point we'll want to do some cost optimization because it's very likely we're giving things a lot more memory than it needs even. And it's hard to say like with different data sets, how much like if there's like recent data that's recently written is also going to be hot data, or if we're going to be doing a lot of digging through old data to find what we need and things like that.
Interesting problems to solve.
Yeah. Yeah, definitely very fun.
Because I think the design of RocksDB is such that even when you see universal to get to
Right.
model, yeah, so.
It's funny that you mentioned that React used LevelDB because everyone should, Brian Hunt, right?
Yeah.
Yeah, every once in a while he'll drop in our channel and say like if we got a weird crash, he's like, oh, this sounds a lot like a LevelDB thing. If the something got corrupted, and like that lines up.
Yeah, residual is not really smart. For other, in some ways it's too clever, but also that LevelDB was Google through the wall kind of situations, or it was a couple engineers that Google wrote in. I think let's just share this. And so one really
Yeah. Well, even RocksDB has some really weird edges where like, especially when it comes to performance tuning and all the options. I think I can't remember the quote in the documentation, but it's something like they write like even us like RocksDB developers don't know like the right setting for this thing. Something.
Yeah, I remember like first version, one version early decided to spin up 72 threads to handle PD or a low PD request. Pretty thought for everything. Mostly one of tries. Low dependency on that.
Yeah. I'm trying to think for reads, how many processes we end up with. I think it ends up, because we're using the Java, it all comes in over the gRPC Java thing, which I think by default uses I forget what the executor is called. It's the one that has no caps on threads, where it's just like each request will make a new thread. However, since we're using gRPC streaming, it ends up being like one request per connection, basically. And then I think that's like static more or less. So it'll like if you had a new client, it would increase the connections, but it's not like request volume increases connections. But it's probably, I don't know, hundreds of threads maybe, and I haven't seen any kind of like read contention or anything like that.
Yeah, well, you're also not trying to predict so.
Right. So with level, is it written in C or something? C++. Okay. Do you know, because I know that RocksDB is related to LevelDB. Do you know, was it actually like a
I think it was a fork.
fork? Okay. Yeah. I know there's definitely shared history there.
It's like yeah, because of the sound. It was simpler. Smaller. There was basically one or two.
Yeah. Yeah. So far, RocksDB seemed pretty solid. can't think. And they keep, I think recently too, the Java libraries that they provide have been getting some good love, and there've been some optimizations around the buffers. I think I don't know enough about Java buffers, but there's like a direct buffer, an indirect buffer or something. And I think one of them, like, you can pass the buffer to C and it can like write into that memory rather than having to like traverse the JNI twice or something like that. I think there's some new stuff around that to reduce allocations and.
Yeah, there's some newish stuff that developed, like, cache memory.
Right.
But.
Interesting. That might be interesting. Yeah. I guess there wouldn't be much benefit over, like, if we're just allocating them up front. Big boots, right? Yeah, same idea. Interesting. Well, if there's no other questions, that's all I got, and I'll stop sharing. Still glad to chat about anything, but